Okay. Um, I've gotten a couple questions regarding the test. Basically, I'm not gonna say too much. I want you guys to try just try working through the prompts and try giving as complete an answer as you can. Um, don't worry too much about like I don't want to say this. Don't worry too much about making all your work nice. Like, okay, so you try to make your final solution as neat, not just neat, but like as well presented as possible in terms of like the writing. But I also want you guys to show me your work, right? I want to see a thought process because for a lot of you, this is the first time you've been asked to really sit down and do a test where it's like, okay, the questions are kind of easy, but like if you actually want to show all the work, it starts getting kind of complicated, right? And some of the reasoning starts getting tough. So I want you guys to show me like work so I can kind of see like, okay, this is where you're kind of going wrong, or this is where maybe you have the right idea, but you're not thinking about the process correctly. You know, that kind of helps me judge and give you feedback on some of these questions. The questions I marked as difficult, one of them is actually difficult in the sense of if this is your first time seeing that sort of problem, it will take a while to work through, but it's not too bad. The other question is difficult in terms of just there being a lot involved in the proof compared to the rest of the test, right? So the first question that I marked as difficult was the one about the new logical connective, the one that looks like this, right? Where this is true if and only if the and q and statement is false, right? So that one, I request that you guys, write every single logical connective in terms of this, right? So what I mean is like you can group the P and Q however you want, right? But I'm saying when you define each of these, don't use any symbol other than this symbol and the statements themselves, right? That's what I mean by that. But you're welcome to use our definition from previous lectures to kind of split this up, right? So for example, what I mean by this is, for example, this is defined as, so like if I have P if and only Q, that's the same as P implies Q and Q implies P, right? So if we look at this, if we've already defined this connective in terms of this, and this connective in terms of this, you can kind of look at how you've defined it and just put it all together, right? That's totally fine. You can use the reference. You don't have to see how do I do this straight from here, right? You can build it up using previous operations that you've already defined using the new connective. So don't forget that, right? You don't have to build everything from scratch. The whole idea is, we kind of build a lot of connectors from previous connectors, perhaps. So we can use this guy in the previous iterations to find the more difficult ones, right? Same thing with P implies Q. If it's hard to think about what it means for P to imply Q, write it in terms of the first three connectors, right? We've seen a way in which we can write P implies Q in terms of just not, and or, right? So essentially do something like that. For the other difficult question, I got a couple questions about this one. This is the one where I wanted you to show that given two equivalence relations, their composition is an equivalence relation if and only if it's commutative, right? S composed P is exactly equal to P composed S. Now, a couple of things. So I did answer a couple of these questions in email because I wanted to have a chance to go through it today. So the first thing is I gave you guys a definition of composition, right? So you guys are not expected to go and look up, oh, what is the definition of, let's find this in a textbook or something. That's not what you should be doing, right? Since you've already been given a definition, that's what it is, right? Even if I somehow, so the way I define it is a standard definition for composition of relations. But even if it wasn't the definition, like if I gave you a definition that was completely different from the book or whatever, you would still have to use that, right? That's the whole point of math is if someone tells you here's the definition, you shouldn't be like trying to go through other places and be like, okay, does this match up? Sometimes it's just more. Sometimes you're being given a different definition, right? And I haven't done this yet, but I might in the next quiz and test where I will give you a definition perhaps that does not match with the actual definition, no matter how hard we try to force it to match. So the idea is I want you guys to kind of lean away from the sense of, oh, okay, I need to find other sources that talk about this, or I need to find other sources that discuss this particular new definition or new topic. You have all the information with you, right? So you want to solve these problems using only the information given, and then just use your proof techniques, right? Use your reasoning, use your proof techniques to figure it out. I'm trying to get you guys to move away from this whole idea of, okay, I need to have seen an example before I solve it, right? And this is a good example for this. This is a good question for this, because this is something that's well defined, right? Composition of of relations is well defined, but it's actually quite hard to find a good definition elsewhere, and there's not a lot of problems and theorems out there in books talking about composition, right? So this is a good theorem to give, but at the same time, it really tests your understanding of what you're actually doing, right? It kind of splits apart the people who understand sort of what's going on, but you're kind of used to, okay, I want to see an example for doing it that will work, versus the people who are like, okay, I don't care about what I've seen before, I don't care about what I know, I'm just going to sit down, look at the definition and work through it, right? Because the only way to prove something is by the definition, right? So I have a definition, I know how to talk about composition, right? So, let's talk about what is required of this question, right? You just ask to prove that this is an equivalence relation if and only if the statement, right? So just to remind you, when we have an if and only if, there's two things we have to prove. There's forwards and a backwards direction, right? So immediately you already have two halves of the page or two halves of the proof that you need to fill in. One might be easier than the other. Well, okay, I'll tell you, one direction is definitely easier than the other in this case, but I won't tell you which way. Another thing I want to mention is people ask me what this equality means. Remember, when you're trying, a lot of people say like, wait, these aren't numbers, how can they be equal? Remember that we use this sign for a lot of different things, right? We use the equal sign for different things depending on the objects. So if we talk about numbers are equal if they're exactly the same number, right? But then we say something like sets are equal if they're both subsets of each other, right? So we don't say, okay, so there's two ways to talk about set equality, right? We can say that A and B are equal. So for example, if I have these two as sets, right? They're equal in two senses, right? The more informal way of doing it, not in proofs, is just saying, oh, every element is an element of the other set, right? So one shows up here, two shows up here, but these are equal, right? So if I call this A and call this B, right? I can say that they're equal because A is a subset of B and B is a subset of A. And that's what it means for them to be equal, right? And so to show that two sets are equal, there's only ever one way to do it, right? There's only ever show that they're subsets of each other. In other words, how do I show that A is a subset of B? Well, we talk about the definition of the subset, right? We said that this means that if I take an element of A, then it's also an element of B. So if I'm trying to prove this statement, well, it's easy. I assume that X is in A, and I do some work and show that it's in B, right? So for instance, if I want to show that this set is a subset of this one, I'll pick an element from here and see if it's in here somehow, right? So that's what you want to be doing, right? So you need to remember that there is always a definition for every symbol, every word you're looking at, and you really need to understand which object you're talking about, right? So before we even go into what the connectives are, what the relations are, and stuff like that, maybe relations is not a good word, maybe the connectives, equality, formula, disjunction, stuff like that. You want to think about what objects they're comparing, right? Because the objects tell you how you work with them, right? So saying two sets are equal isn't the same as saying two numbers are equal, maybe not even the same as saying different, for example, even if I have something like the cardinality of S, is 3, right? That's fine if S is a set. But I can't say S equals 3, right? I can just say, oh, it's equal because that's the number of elements in here, right? I can't compare a set with a number, right? So, however, if I define maybe S as something like this, I can say S equals 1 in the sense that we sometimes use the number 1 to describe the definition from the set. When we saw we were building sets up from natural numbers, that's kind of how we did it. You'd want to do something like that, right? Oh, I guess that was 2, not 1, sorry. But the main idea being that you have to be careful about equality. You can only compare 2 different sets, and different numbers of symbols and whatever, they might represent different types of objects depending on the context. Right, so that's a really long ramble just to say be very careful about what you're comparing. And whenever you ask yourself, okay, how do I show these things are equal? Well, don't wait for someone else to answer that question. You really have to ask yourself, right? So what are the ways in which we show these things? It's always from a definition somewhere. Okay. So past that, if you guys have any other questions, feel free to ask me about that for the test, and then once you've given it to me, as usual, I'll try to grade it as properly as I can, and then you guys will get my feedback on that. Okay. I guess I should ask. If you want a solution set for the test, let me know. I'm not gonna make one. I'm probably not gonna make one unless more than a few people ask me, but you're more than welcome to discuss the test with me once you're done. And if you want to see how I would do it, I'm happy to show you one-on-one. But if more than a couple people say it, then I'll make a solution set. But otherwise, I probably won't. Same for the homeworks. Okay. Anyway, today we're going to be starting a new section. Right? Obviously, we're done with the proof section. So now we're ready to dive in to essentially each of the introductory topics that you'll see in mathematics, right? So I'm going to call it abstract algebra. I personally think this is a better name. Other names you'll hear for this course, here at they call it foundations of algebra. I really don't like that name. Some of the people call it modern algebra. Also don't like that because when they say modern, they really mean like over 50 years ago and more. It's just because people have been calling it modern algebra forever. It's not really modern anymore. In fact, quite a bit of it is dead. A lot of it has been like fully solved. At least a lot of the smaller parts of the algebra course that you will learn in an undergraduate degree is not stuff you would go and do out in the world of mathematics just because it's all already to completion. So abstract algebra, I think is a better name. The word algebra itself might not even be a good name. A lot of people call this class structures, mathematical structures, which is a more apt name, but everyone basically calls it algebra. Like if you tell someone you're taking an algebra class in a math degree and they do math, they'll know what you're talking about. But it's also not what algebra means. We'll talk about what an algebra means, but it's probably going to take us until Wednesday or Friday until you have enough build up to actually know how to talk about what an algebra is. But okay, so what exactly are we doing here? So let's think about some of the things we've done so far. We've talked about sets, right? And we've come up with these sets that we're used to, right? But when I talk about a set, it's just a collection of elements. I'm not talking about how the elements relate to each other. It's just I have this box of a whole bunch of things in the box, but none of them are connected to each other. I don't have any way to connect them and see what happens when I put them together. It's just I have things in a box and that's all, right? So in mathematics, a lot of you, what you're used to is doing computations, right? We are looking for ways to put numbers together, to put objects together and stuff like that, right? So we need a way to do it, but since all we've done is set theory, we don't really have a way to do that yet, right? We don't have a way to really say, okay, let's take things and put them together. All we've done is say, okay, we have a set. So that's what we're going to start with, right? So let's give you a definition. So let S be a set. Right. we say that a binary operation right, is a function. And here, a lot of people would, you can throw whatever symbol you want here. The symbol doesn't really matter because the operation is going to change later on. For now, I'm going to use a dot the same way you've seen multiplication. So it's a function. We'll label the function as a dot. S cross S. So what does this mean, right? We've talked about function, we've talked about notation. So the idea is, what is S cross S? That's the Cartesian product of F. In other words, it's all sets of ordered pairs, right? Such that you can put them together, or when you pick that ordered pair, I can spit out something else in that, right? So this is where a lot of people start getting confused when they see this notation. Remember that this notation for functions only talks about what the domain and the codomain have. Just because you see the same letter doesn't mean it's a sense of, oh, you have to keep the same numbers, right? Like, for example, if I say f is a function mapping from R to R, I can have f of x be equal to x plus 1, right? And first of all, this is bijective, right? So it does hit the entirety of the domain and the codomain, but it's not like just because these two letters are the same, f of 1 must be 1, right? In fact, f of 1 is 2. So remember that these just represent where you're allowed to be. That's what I'm doing here, right? And again, it doesn't have to be all of it, right? I could say this is 2x, in which case this wouldn't hit every single real number, right? Well, oh, sorry, it does hit every single real number. Maybe this, right? This wouldn't hit every integer, right? Because you would only get even integers on this side. So when I say S cross S to S, all this means is that this gives us a way to take two things in a set, put it through this function, whatever it is, and output something else. So this is where we get the operations you're used to, like addition and multiplication, right? So addition is a binary operation on the real number, right? So addition and multiplication, as you're used to, are these sorts of operations. Maybe on R, on the integers, on the rationals, you know, whatever you want, right? On sets that you're used to. These things are binary operations. I mean, technically, so are subtraction and division, right? I told you before that, oh, don't worry about subtraction and division. We don't really want to think about that. Well, if I'm just talking about binary operations, those are still binary operations. I take two things together and see what comes out, right? But then division gets really weird because we always say you can't divide by 0. So it's like, okay, now we have to take things out of the set because, you know, a function has to include all elements of the domain. So if we're talking about the real numbers, all of them, division is not a binary operation because I'm not allowed to plug in 0 into the second coordinate, right? So we have to be careful about stuff like that, but really that's all it is. Here, before we go on, and aside, notice I'm very specific and saying, oh, this is just S cross S, right? Here's what I always ask people. And this is, you know, something I ask within the confines of a math class where, you know, I keep saying this over and over again. I want you guys to only use what we've built up so far, right? We've built up these things to sets, we have these definitions. You know, when you write something down, it has to come from the definition, right? So I'll ask people what this is, right? And I'll give you like a couple seconds to think about it. Or if you're watching this asynchronously, pause the video and actually give it a good think for a second. And say, okay, does this have an answer? Well, most people are going to say this is 6, right? You'll be like, well, 1 plus 2 plus 3 is 6. And I'm just going to tell you it's straight up wrong, right? This doesn't make sense. What I wrote on the board is nonsense, garbage, because I haven't told you like this. What this is if this made sense, that would be an operation that takes 3 things and spits out 1 number, and we can't do that. All we have is binary operations. We define addition as a binary operation between 2 things. So when I do this, I have to tell you what order to do it in. So this would be 6, and this would be 6, right? If I use parentheses to tell you what to do first, so for example, in logic, we maybe talked about how you should use parentheses before your other connectors and stuff like that. That comes first in the order. Same thing here. I have to tell you what order to do it in, right? I have to tell you how this works. So that's part of what it means to be a binary operator is I can only take 2 things and put it together. So now that I've taken these 2 and put it together, now I have 2 things to put together overall, right? And a lot of you are saying, wait, this is kind of dumb. Well, we know things are associated, that we've learned before that things are associated. Why does it matter how we group? And that's why I say, wait, we haven't talked about associativity yet, right? We haven't defined what it means to be associative, and we don't know if things are associated, right? We haven't built that up. This is the first time we've even seen anything about operation, right? So you have to be careful about that. This is why I always stress it, right? I think a few of you might find it weird or stupid how I keep going on about how, oh, we're only allowed to use what we have built up so far. But in reality, it's actually much harder to do that than most people think, because there's so many things that you take for granted that you don't even realize you're taking for granted, because you've been told that numbers are associative almost as long as you've been alive, pretty much. And it's like this is something you were told because we're only working with, for example, real numbers, right? But when we're building things up from scratch and we're talking about operations and stuff like that, we can't just assume it, right? We have to know what these things are defined as before we talk about it. And the obvious question next is, okay, fine, give me an example of something that's not associated. Why do we care? Why don't we just say everything's associated? Well, an operation is just a set, right? So let's come up with an example of a non-associated set. Well, I'm using what associated in the sense that you guys know, right? We'll define it formally in a little bit, right? But for now, let's just look at an example of why we care. For those of you who might want to teach math later on, or are going to teach like undergraduate mathematics later on, you will notice that as I start these newer topics, I always give examples before the definitions. And I think that's very helpful and important in teaching, because I think you just define it and give examples of it. It's not a bad way of doing it, but giving examples first maybe motivates why you might want these definitions to exist, right? So for those of you who want to go into teaching of some sort in terms of like pure math and higher mathematics, I always recommend this idea of give examples before you give definitions. Okay, anyway, so example of something that might be non-associative, we'll talk about what that means formally later, but for now, it's what you think it means. So let's play a game of rock, paper, scissors. Right? And we can define a binary operation as who wins when you play, right? So essentially, I'll make a list. So we'll define this operation, right, using this table, right? If rock plays rock, we can say no one wins, right? But we can also say that we'll just define it as itself. What's important is what happens here, right? Paper beats rock. Rock beats scissors. And scissors beats paper, right? And instead of rewriting all 9 possibilities, I'm just going to say that it's commutative. In other words, I don't care if rock plays paper or paper plays rock. I don't care about the order. Because remember, this guy cares about the order. These are ordered pairs, right? So it doesn't matter. But I'll claim this is commutative, right? And so that saves me the trouble of having to define every single pair. Right? And again, I'm not going to define commutative. We're not just think of it as what you know it means. 1 plus 2 and 2 plus 1 are the same, right? So rock plays scissors and scissors plays rock. There's no change in the outcome. It's going to be rock. Well, let's look at this then. I mean, this is just here to kind of like formalize it a little bit, but obviously we don't need it, right? All of you know how to play rock, paper, scissors, so we can kind of think about what this will be. So using this, this function will give an output, right? So that's why we have an equal sign here. So here, rock plays paper, the winner is paper, right? And when paper plays scissors, as the result of this, the result is scissors, right? But then what happens when I write the same thing, but I move my parentheses around? Now, when paper plays scissors, scissors is going to win. But when scissors plays rock, rock wins. These are equal. This is a binary operation where you don't have associativity. These two things are the same, right? So we've got a problem. And so structures like this is why you care about associativity as part of something we're going to include in the action to describe the structures we're going to talk about. And it's not something you can take for granted. Some of you might be wondering, okay, fine, you've given this really weird example of rock, paper, scissors, fine, whatever, it's not associative. But surely everything maybe with numbers and mathematics, surely that's associative. And you need to go to these weird examples to find non-associativity. Well, that's not true, right? For those of you who've taken Calc 3, the cross product is not associative. Depending on what order you put your vectors, taking cross products of 3 vectors is not associative. So even then, we already run into the issue of not being able to just write out what is A cross B cross C in terms of vector calculus. Can't do that unless I tell you what order to put it, right? So that's why we have to be careful about stuff like this. So this kind of gives you a glimpse of the fact that when we talk about sets that have nice operations that we want to talk about, maybe there's some rules that we want to put on it. Maybe there's some things that we want to say about it. For example, in the real numbers, right, we always talk about, what's kind of the most important number. Some people would say it's 0, or some people would say it's 1. There's really nice properties regarding 0 and 1 that show up a lot. So maybe that will come in somewhere. So that's why we will first talk about something called a group. So in abstract algebra classes, there are some people who teach groups first, and then what I call rings. And some people who teach rings first and then groups. I'm going to start with groups because if we're trying to build this very mathematically and from the ground up, it makes more sense to start with groups because the ring is just a group with additional things. You will see sometimes, a lot of times, there'll be an abstract algebra course taught for not just pure math majors, but also math education majors who are going on to teach. And so for a lot of these people who haven't really seen a rigorous introduction to mathematics, it might be more common to start with rings just because a lot of the objects that we work with are rings, right? Real numbers, integers, stuff like that, they are rings. It's easy to start with that and then motivate groups later on. But for now, because we're building everything from the ground up, we're going to start with groups and keep putting on extra conditions and seeing what we get. So our first actual definition in mathematics, right? A lot of the definitions that we talk about now, up to now, like have just been preliminary definitions, or even here, this is a preliminary definition for groups, right? We'll see now, this is where we can really start. Okay, these are the definitions that you need to know for these various fields. So a group, right, is a set equipped with a binary operator or operation. And maybe I'll say this is a set, maybe we'll call it G for group, right? And maybe I'll call the operation this same dot that we'll be using, right? And we'll denote this as an ordered pair. Typically, when we define a group, we kind of have a set, we have a set and an operation, right? So people would generally define it as an ordered pair. As we start getting more used to this though, we'll start referring to it as just the group G, right? And we'll just use that as shorthand because I don't want to have to keep writing this out over and over again, but this is what that means, right? But once we get used to this fact, We already know what the set is. We already know what the operation is. Once we define the operation, we say, okay, we just have a group. We're going to just call it G, right? You'll see me do this in shorthand in later theorems and proofs, but every single, if you want to be really formal, this is what shows up every single time. A group is exactly denoted like this, right? We might use shorthand, but we mean this. Because a group encapsulates two pieces of data, the set and the operation. Such that we have technically four properties. I'll tell you why I say three here in a bit. Okay, so I'm just going to write down three properties, and here's what they are. For every A, B, and C in a group, we have the A dot B dot C, A dot C. That's obvious, that's associativity, right? Okay, what about the second one? Well, for every, there exists an element, we'll call it little e, and I'll talk about that choice in a little bit. It just gives such that for all little g in the group, right? When I put it together with E, regardless of the order, I get back G, I get back that same element, right? And this little e is called the identity element, right? We use little e the most common to talk about the identity element of a group. Some people, even if you're not dealing with numbers, some people use 0, right? Because that is the additive identity, right? Anything plus 0 is itself. But the problem is I didn't call this additional multiplication, right? And so I can think about 1, right? 5 times 1 is 5. Anything times 1 is itself. I have that same sort of identity property with 1 and 0. So we're going to refer to 1 and 0 later on, right? So when we talk about sets, so rings very briefly are sets with two operations, right? And you want to think about these as addition and multiplication essentially. But here we'll use little e, so there's no question about what type of identity we're working with. But later we might have to differentiate between 0 and 1 in some way, right? So you will see some books use 0 or 1 as an element for the identity. I would highly recommend not doing that because it will cause confusion. Okay, anyway, so this is the identity, right? This is the formal way to define it. And finally, we take any element on A. For any element in G, there exists an element B such that when I put those together, again, doesn't matter which direction, my result is the identity. And will denote, by definition, whatever this B is, will denote it as the inverse, right? So I'm not telling you what an inverse should be, I'm telling you what it must be. I'm defining this inverse for you, right? I'm defining whenever you see an element with this -1 symbol, that means it's exactly this inverse. So this is a formal definition of a group. Some of you who have seen algebra before or have taken algebra before are right now probably asking me, wait, every single book I've seen uses 4 definitions. You have 4 properties, well, 4 axioms in a definition of a group. Why do I have only 3 here? And those of you who maybe remember what you've seen before will ask me, wait, you didn't use the word closure at all, right? And this is something I used when we were talking beforehand about integers, right? Well, I talked about how, addition and multiplication are closed in the integers, right? And so there's some sense of closure, right? So sometimes you'll see books that talk about a property called closure, and that would be that for all G and H in G, G dot H is also in G, right? But those of you who are perhaps even more observant might notice that this is embedded in the definition for binary operation. Because when I called it a binary operation, I said that when I took two things and put them together, it comes back with something in the set. So that thing of closure, that this definition or this axiom, this is completely embedded in how we define functions, right? We define functions as having to take everything in the possible domain and map into something that's still within that set, right? So that's closure is already in here, right? So that's why I haven't included it here. A lot of books you'll see will just talk about, oh, okay, a group is a set equipped with an operation, right? Maybe not a binary operation, but there's an operation that puts two things together, and then you will give the four properties. I think it's better to talk about this as a binary operation just to make sure that we have this closure that's just inbuilt into the operation, right? There's some operations later on in math that you will see that aren't binary, right? We might talk about operations who, when you put two things together, it falls into something outside the set. But for now, since we're only building things up from one set, there's no other set we can work with, right? We only want to work with the current set we're staring at. So some of you might have seen closure as a definition. You can put that in, you can think about that as if you want, in terms of group having four properties, and they do, it's just inside here, right? So, you know, if I ask you to check if something's a group, you can think about it checking four things: associativity, associativity, closure, identity, and inverse. For the most part, the order doesn't matter. However, notice that in the inverse, I use the identity, right? The identity shows up in the inverse. So if I haven't defined the identity yet, I cannot define an inverse. I need to first have an identity before I can talk about what the inverse is, right? So what are some examples of groups? Well, right here, we already have groups, right? We have the row numbers, integers, the rationals, right? These are groups under addition, right? Now, what I'll have to do is, instead of just writing these down, right, I have to be careful. Right, I have to write them in this format, where the plus is the regular addition you're working with. Right. Now here's a problem. What about this? Where this is the standard multiplication. And ask, is this a group? Well, we can run through each of these things, right? It's closed, right? When I multiply two row numbers, it gives me back a row number. We do have associativity, right? Multiplication is associative. And in fact, we do have an identity, right? What number, when we multiply, gives you back itself? Well, 1, right? Anything times 1 is itself. But now the problem is the inverse. You know, most people did tell me, wait, yeah, if I take A and I want an inverse, well, I can just write 1 over A, and this will always give me back 1, right? And so for every element, I have an inverse that gives back a value. But then I can ask another question. What if A is 0? 1 over 0 doesn't exist, right? If I give you the element 0, there's no number in the row, there's no row number you can give me such as 0 times that row number is equal to 1. So this has no inverse. So this is not a group. So the row numbers do not form a group under multiplication. But then some of you might be saying, wait, yeah, 0 is the only one that doesn't work. So what do we just throw 0 on? Let's just not include 0. Right, so for those of you who might not remember, this is just a set difference notation, right? I'm just taking out an element of the set. So I'm just taking out the set containing 0. In other words, I'm just taking the element 0 out of the row numbers. Well, now this is a group. I don't have that issue with 0 not having an inverse. I've taken out 0. And 0 wasn't the identity, right? It's the additive identity, but here we're talking about multiplication. So I haven't removed anything important because I haven't removed an identity, and so this is fine, right? It seems stupid to say, but I can have a group with one element, just the identity, right? And I write E here because it doesn't have to be 0, it doesn't have to be 1, it doesn't have to be a number. This with any operation, this is what we call a trivial group, because it really just has the identity. Which makes sense, right? If I just have the identity, we know how this works by default. And so obviously associativity and closure are going to work because everything's going to give back itself. And if that's the only thing, well, the inverse is itself, right? So it really has only the one element because no matter what you do to this element, nothing changes. It's always going to stay as that same element, right? So when you see people talk about the trivial group, they're just talking about a group with only one element where that element is the identity, right? So we have a lot of these groups that we can talk about, but they don't just have to be these sets that we've seen, right? I can create a new set from numbers that we can look at, right? I can create a new set from just a set of values, right? So for example, right, let this be 0, 1, and we'll say this is defined as, so this maps, let's say 0, 0 will map to 1, 0, 0, 1 will map to 1, 1, 0 will map to 1, and 1, 1 will map to 0, right? This is how to define the operation. And it turns out that S with this operation is a group. For those of you who've seen field theory before, this is a field of two elements. This is Z2 as a group, right? That's how it works. But essentially, I don't have to call it Z2 or any fancy names that you might recognize as what the structure is, but I just have a set with elements in it, and I tell you how a certain operation works, and you can check whether or not it's true. Well, I didn't tell you what the identity was, but it should be obvious that the identity is 0, right? You notice this, when I had zeros, nothing changed. I kept the other guy the same. But when I put 2 1s together, that changes back to 0, right? So this is the identity, and then each of them have an inverse, right? Each inverse is itself, right? 1 with 1 gives back the identity, 0 with 0 obviously gives the identity, right? So that's your, each of these elements are their own inverses, so inverses do exist, and you can check associativity for yourself. So that's the idea, right? We have a group, we can construct a group just like this, right? What are some other things we can talk about? Well, here it looks like I've been giving you sets with operations, and you just be like, oh, here, this is a group, right? But the whole idea is we can use groups to describe mathematics. So one of the reasons people study mathematics is people use mathematics as a tool to describe real world operations, right? Things that happen in the real world. We can use math to describe how something might work. So for those of you who've taken linear algebra, you might have seen, okay, if I'm rotating something, how can I use a matrix to represent this rotation? There's a lot of these representations that you can look at that will work out nicely. Now, let's look at this, using the language. So we can talk about something like a square, right? So let's draw a square, and I'm going to label the elements. Right. So maybe I want to represent, maybe I have this object in the real world and I want to rotate, right? So maybe I want to rotate and I want to reflect across some axis. We'll just say flip, right? So essentially, maybe if I flip it this way, I might flip it this way, and so on and so forth, right? So the idea is there's maybe 2 types of reflections, but we'll talk about that later. But now we'll just treat it as reflect across this line, for instance, right? So maybe if I rotate, I can get to something like this, right, when I rotate it clockwise, and then flip, and so on and so forth, right? So I claim that this forms a group. So what does it mean for that to form a group? Well, it means at first there has to be binding operation. So now we're kind of thinking about, okay, let's just think about whether or not this is a group and see if we can come up with all these things. Whereas before, I gave you the operation. Here, you might see the operation as obvious in like real world terms, but you want to somehow turn it into a system, right? Because I gave you a shape here. I didn't give you a set, I gave you a shape. But if I want to turn this into a group, right, maybe my set is the set of all vertices, right? Here I can label the vertices 1, 2, 3, 4, and or I could label them A, B, C, D, and whatever, but I can put it into a set. And my operations, I can tell you, you know, how this works, right? So maybe my operation will be what happens when I put two things together, right? So first of all, it doesn't make sense to say, okay, what happens when I put this square with this square? That's not what we want. So maybe our operation is really how these things work together. So my set is maybe the set containing all of these, but my operations will be functions that change this in some way, right? And I claim that each of these things might be a rotation, it might be a reflection, or might be a combination of these, right? So in fact, this might not be the correct set. However, what I might want is maybe the power set, right? So 1, 2, 3, 4 perhaps indicates this configuration, right? So maybe I want some order to that. Maybe I want an ordered pair, 1, 2, 3, 4. Because now, if I maybe write 4, 1, 2, 3, that indicates maybe something about, okay, let the first element be this top left one. So this will be this square, and the second one will be this second square right here. So those represent two different objects, right? But some objects might not exist. There's some weird twist that I can't do, right? If I did something like this, you can't get this from a rotation or a reflection, because what did I do? I just took this and flipped it like that. You can almost think that if this was like a rubber band that you're using to like rotate or flip around, this would be like a figure eight, right? I flipped one side of the rubber band, and so in real life it looks something like that. That's never going to look like a square, right? So maybe this 1, 3, 2, 4, maybe this won't appear in the group, right? If our operations are just rotation and reflection in some way, right? So this is, and we'll talk about this in a little bit. This is called dihedral group, right? We need a little bit more to discuss kind of the specifics of this, but we'll get to that on Wednesday. But for now, you know, these are some of the kinds of things we can do with the groups. Another example of a group that, again, I'll talk more about on Wednesday is what we call the symmetric group. And usually this will be denoted as n, where n is just a natural number that you pick. So you have like S2, S6, and so on and so forth. And essentially, the set for this group is the power set of all ordered pairs of a certain size, right? So for example, what I'll have is, I'll say, for example, S3 is all possible permutations. Some of you might have heard this word before. It's all possible permutations of 1, 2, 3. So I have 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, 2, 2, 1, right? So some people also call these permutation groups, but really they are symmetric, is what we call it, right? So we talk about the ways in which you do all this. So you might almost see a direct connection between this and dihedral groups, right? Where here, I can label a polygon with those numbers, but now there's no restriction on my polygon, right? There's no restriction on how I can twist things. So for instance, let me just maybe write out all the possibilities. And we'll notice something here. Previously, when I talked about dihedral group, I just talked about, you know, you have a shape and you rotate and reflect. Well, if I have 3 vertices, that's a triangle, right? So what if I looked at the dihedral group for a triangle? Notice, because of the triangle, there's no problem with like flipping or twisting something. So I can get all of these. So that set of the dihedral group for a triangle contains exactly these 6 elements. And remember that the operations that we had, we're just talking about a set, right? So the two things can be the same set. So a lot of people at this point might be wondering, okay, if I took the dihedral group of, we'll call it 3 elements, right? The dihedral group on 3 points. A lot of people ask, okay, you know what? I'll do it this way. I'll do it this way. I'll give a more formal definition of this on Wednesday. But people ask, are these the same? Because when I looked at the dihedral group in terms of the rotations and reflections of the triangle, I get exactly the same elements. So you think, okay, it's a set. They're both subsets of each other. Are they equal? So we can ask, is the dihedral group on 3 elements, on 3 vertices, exactly equal to the symmetric group on 3? Because they work in the same way. In fact, the operation is the same thing, right? The operation is always the whole changing of how the vertices go around. The answer is no. They're not the same. Because when I say that they're the same, I really mean they have to be exactly the same group. It means I have the same operations, I have the same set defined. And even though there's a similarity between how they work, they're not the same, they're not defined as the same thing a priori, right? What I really did was I formed in your mind a connection between these two and a similarity in how they work, but that's more of an analogy than anything, right? Just because it's an analogy doesn't mean they're the same object, right? So the idea is, we'll instead say that they're isomorphic, and we'll use this kind of swiftly. You know, you're used to that being approximate, but now you're going to start seeing this. These are equivalents, right? So this is to the equal sign with the bar above it, with the squiggle above it. We call these isomorphisms. Once again, we're going to define these more formally later on, maybe today, maybe Wednesday. But now, when we talk about equality of groups, 2 groups are equal if they're the same set with the same operation. It literally has to be exactly the same. Now, there's a lot of groups that will look similar to each other, right? So, for example, if I took this group and instead replace this with letters, I can define the group the same way using letters. I'll say A, B, C, B, C, A, and assign an order to these letters in a certain way. And we can say, okay, these are isomorphic. They're not the same group because the set isn't the same. One is 1, 2, 3, the other one's A, B, C. They're not equal. But they can be represented the same way, right? When I have numbers representing for A, B, C and stuff like that, that's when we have this equivalence, isomorphism, right? The isomorphism is, in essence, a way to talk about groups that they're essentially the same group without actually being the same group, right? So that's what I want to introduce. So the reason I'm doing this is I want you guys to have, at least have a taste of why these are important before I define them later on. But we'll get to that later. I don't know how far I'm going to get today. Let's see what time it is. Why can I not see what time it is? Okay, it's almost been an hour, so I'll probably get to isomorphisms on Wednesday. But for now, here's a couple other definitions that we can look at, right? So first, we've defined a group, but you can almost think that, for example, these are both examples of groups that we looked at, right? The real numbers under addition and the integers under addition. But a lot of you will have noticed something. Z is a subset of R, right? The integers are a subset of R. So is there a way we can talk about these in the same way? So we call this a subgroup. Right. The subgroup is a subset. So I'll say a subgroup of G, right? So again, I'm going to change, like, I'm going to write this here. I'm going to say let capital G be a group. And I'll note 2 things here. The first is, notice I wrote G and not G comma some operation, right? So this is what I mean by shorthand. A lot of people you will see in both questions and homeworks and later theorems and stuff like that, they'll just say let G be a group. But really what I mean is let G with an operation be that group, but you can really just call it G, but that's fine. We know what this means. We know that a group isn't just a set, it's a set with that operation. So let G be a group. A subgroup of G is a subset, we'll call it H, which is a subset of G. Subset H is itself a group under the same operation. And by same operation, I mean whatever operation we're using to define G, we'll use the same thing when we're putting things together, because, well, when we define the binary operation, we say this works on everything from the set, right? Well, if I take a subset, of course it's going to work, right? It's still a subset is still within the set. I still know how to put two things together. But now, to make a group, now that set has to land within H, right? So we could look at closure. This may be why it's better to include closure as one of these four, right? And that's why a lot of books do include closure as one of the four actions here, because now it's no longer the same quote unquote binary operation, right? Because in one case, a binary operation here is, so let's use G. The binary operation is from G to G, right? Where this might be the codomain, it might be the range or whatever. But now, in my new thing, I need my binary operation to be this, right? I need to go within the subset. So I still have to check closure. This is definitely the same operation as this, right? But it is definitely possible to have something that's a binary operation here, but not here. What's an example? Well, take for instance, odd numbers, right? So let's use regular addition. If I add two odd numbers, it no longer falls within the set, because when I add two odd numbers, I get an even number, right? So if I'm considering, say, a set of even numbers, that's fine, right? The set of even numbers is a subset of the set of integers, right? And when I add integers together, there's some way to do this, but when I restrict that to only the even integers, I still get back even integers. But if the subset was the odd numbers, well, something's wrong now, because, for example, 1 plus 3 is 4, and 4 is not odd, so this fails, right? So when you're checking to see if something is subgroup, and part of the definition of this being a subgroup is I need that closure, right? And that's one reason why a lot of people include this with they make it 4 properties instead of 3. But it's something better to have it as 3 properties, because then that forces you to think about what does it really mean for this to also be a binary operation on this, right? So for example, if something's not a subgroup, so let's look at the odd numbers again. Well, one of the issues is that the same operation is no longer a binary operation on this new set. That's how you want to think, right? Because you can totally apply the same operation. It'll still give you a number, right? Because it will still give you a value from the original set. It just might not be in the subset. So it's not a binary operation, right? So that's part of the definition of a group is it doesn't just need to be an operation, it needs to be a binary operation. Okay? So for instance, now that we have this, we see that the set of integers with respect to addition, is a subgroup, not just a subset, right? Because these aren't sets, these are groups. So it's a subgroup of the row numbers. And generally, we'll write it like this. So here, I'll keep writing this parentheses because we know what the operation is. We use the less than or equal to symbol for this, or the less than symbol. Right. So in this context, using the regular sharp less than or equal to or greater than equal to, that talks about subgroups, right? Some people use something like that, right? I've seen that before, but the idea is it's kind of obvious if you're using the less than or equal to. It's obvious that these aren't numbers, right? Singular numbers, they are entire groups. So this is a completely fine representation, in my opinion. So you notice I use less than or equal to in the same way that we do in the row numbers. So we can write in the definition here, right? A proper subgroup is the subgroup. Again, I'll say let G be a group. I just be checked, just to be clear. So a proper subgroup of V is a subgroup H of G, right? Such that H is not equal to G. They're not the same. So that's why you can see that we have this sort of notation, right? So another thing I want to say here is a lot of people ask me then, okay, if I say not equal to, is it enough to isomorphic? Because we talk about how isomorphism are not equal, right? Well, but here's the problem with that. When we talk about subgroups, we have to use the exact same set and we have to use the exact same operation, right? If you have the same set and the same operation, it is equality, not isomorphism that you're talking about, right? So we talk about subgroup. And by the way, when people say proper subset, they mean like, okay, A is a subset of B, usually you couldn't even have the same thing, right? If it's equal, it's still a subset. Every set is a subset of itself. But when I say proper subset, it's a subset that is not the original set. In terms of notation, I realized I forgot to give this to you guys earlier on. And this is important just because there are a lot of older books do this weirdly. So the notation that we've been using is for A to be a subset of B, we do this, right? And so if A was a proper subset of B, we'd write this. This is the notation we're going to use for this course, and this is the notation I will always use. But if you are using other books for reference and looking at older books, you notice that when they say A is a subset of B, they'll just use this, which is the same symbol we use for proper subset, but they'll use this symbol to mean, okay, it's just any subset, right? So A is allowed to be a subset of itself. And now you might be wondering, wait, so how do we know like the equality or not? Well, what people usually do is they'll specifically put a line through the equality part to say for sure that it's not the same. You guys can see how this will create some confusion. But a lot of older books do use, and it's okay to think as long as you know how it's defined properly. But a lot of older books will use this to mean, okay, subset, we'll just use this, right? If it's proper subset, we'll use this. Either way, the book will always define its symbols before actually using it, right? You will never see a math book that just assumes you know the notation. They'll always make sure that they have a definition for that notation somewhere. Usually on like the first couple pages, you see just a list of symbols, and they'll just use a word for that symbol. So if you see this symbol next to the word subset, that means we're using this order notation, right? Whereas here, sometimes a book would just say, oh, this symbol is proper subset, and you would know you're using this anyway notation that we're kind of used to nowadays, right? Okay, so we're talking about subgroups. Well, I don't want to maybe have to check, the obvious thing is when I want to check whether something is a subgroup, I have to check all four properties, right? I have to check associativity, closure, identity, and inverses, right? Well, turns out we might not have to. So I'll write this as I'll write this as a theorem. And I'll call this the one-step subgroup test. There is a two-step subgroup test out there. And you'll see why I call it one-step and two-step. If you would like, you can go ahead and look up the two-step subgroup test. In fact, I think I might make that one of the homework problems. I would define the two-step subgroup test for you and ask you why it works just the same as what I'm about to give you. The whole point, the reason why I don't usually give people the two-step subgroup test is once you know the one step, you don't really need to use the two-step, right? But I'll kind of briefly go over it and I'll define it properly for you in the homework and ask you a question about it. So the one-step subgroup test. So this says that let G be a group and let H be a subset of G, right? The theorem says that H is a subgroup of G if for all A, B, and H, we have that A, B inverse is H. So notice there's only one thing I have to check, right? And so that's why it's called the one-step subgroup test. Just briefly, the two-step subgroup test, you will see the same wording up here, but instead of one condition, you'll see two conditions. One is closure, right? Typical closure for every A, B, and H, A, B, and H, and then for every A, H, there's an inverse, right? And maybe there's an identity. I guess technically, say that H is non-empty, right? The empty set is always a subgroup. The empty set with an operation always from the subgroup trivially. We don't care what that group is. Well, actually, it's not a group because it doesn't have an identity, right? So just don't worry about the empty set in general. H has to be non-empty for it to even be a group. So sometimes when you see books write down the one-step subgroup test, they'll actually put two steps instead of just one, but the first step would just be that H is non-empty, right? So that's something that you have to consider is you can have this to be true, but the set actually be empty, and then it would be nothing, right? So make sure to check that it's non-empty. So for example, I could say that, okay, so consider this, so let G be the even number. We know that the even numbers form a group under addition. I can say, okay, now take the subset of all odd numbers. Does it form a group? And usually we talk about how odd numbers don't form a group, right? But if I take the subset of all odd numbers within the even numbers, so maybe we'll say something like that, right? So let G be equal to, so let S be equal to a set of even integers, right? Now take H to be the set of elements from S such that X is odd. By definition, this is a subset of X. But there's no elements in the set, this is empty, right? So you will see that if you try this, this will work. But it only works because it's empty, right? So one technical condition in here is this has to be non-empty, right? So that's a whole big aside to say why some people include that other line. In reality, you don't really have to think about that. As long as you know that it's not empty somewhere in here, you should be fine, right? But this is the one-step subgroup test. So in other words, I want to find a way to see, okay, is this still a subgroup? So let's think about, again, we know that the integers are a subgroup of the real numbers under addition, right? So let's let real numbers be our group, and we know the integers are a subset of the real numbers. So now let's check if it's a subgroup. In other words, if we already know the integers are not empty, right? So that's fine. If we take any two integers, right? Can I take this integer and add on its inverse and get a real number? Well, the inverse of an integer with respect to addition is a negative number, right? Negative number plus any other integer, that's still an integer. So this is a subgroup, right? That's how you use the subgroup. Oh, I guess I should say one note. Notice that I wrote this as if it was normal multiplication. So when I said add them together, that might be a bit confusing. That's just shorthand notation, right? Because I don't want to have to say, okay, the group has the operation of a dot. So then I'll write a dot B inverse and something like that, right? I mean, technically I should write it like this, but shorthand wise, if I just say let G be a group, when I put elements together in a group, you can just write them next to each other, and it's assumed to me that, okay, that's what it means to talk about the operation of that group. So for example, if, so this is the slide here, if G is this group, the real numbers under addition, right? Then what I would say is, even if I, let's say we're just looking at this, if A equals 3 and B equals 4, this element AB is 7. It's not 3 times 4. It's whatever the operation of the group is. And here the operation is addition. So AB really means A plus B, right? That's what that means. So just notation there, if I write AB inverse, it just means use the operation of the group, no matter what it is. It could be multiplication, it could be addition, it could be something that's not multiplication or addition, something completely new. It just means use the operation, right? That's part of this let G be a group. It means that I have an operation in there, so anytime I write a concatenation of letters like this, I mean, okay, just use that. All right, so that's one way to test whether things are subgroups. So in the homework, I'll give you some examples of show this thing is a group or not a group, show that this thing is a subgroup or not a group, right? So for a subgroup, you could just say, okay, it's a subset, let's test everything. But this is a smarter way to do it. There's only one thing you have to check, right? So when you're checking if something is a subgroup, it's much easier to use a subgroup test than it is to check all 4 properties of group, but either works, right? So I think this is a theorem. This wasn't a definition, right? So maybe I should prove this, right? So let's look at proof of this. And I think I'll prove this and then we'll stop there for now. And then we can talk more about this on Wednesday. So what do I have to prove? Well, essentially, I have to prove that this statement says H is a subgroup given that this, right? So in other words, in my proof, I can say, okay, we're given this, show that it's a group, right? So in my proof, I'll first say that, okay, given that G is a group, let H be a subset of the set G, right? Let H be a subset of G where G is the set representing the group, right? And let's say this such that for every A, B, and H, a B inverse is an H. So to prove that this is a group, so to prove H dot is a group, in other words, a subgroup, we need to show all 4 properties. So I'll just label them, right? And I'll probably label 0 as the closure part, right? So let A and B be in H. To show closure, I need to show that AB is also in H, right? So if I have that AB is an H, again, I want to show that. Right. Well, we can pick this, right? We know that AB inverse is in H. So I can look at this and say, if these are the only 2 things I have to start with, right? Let's see what we can do. Oh, right. So if B is in the group, there's also an element B inverse also in G, right? So I can almost take something like, actually, wait, hold on. Hold on, I'm trying to think about this. There's some quick way to show this that I'm forgetting. Oh yeah. Right. I can say let C be in C inverse. B equal to C inverse, right? Oh, sorry, B inverse. Right. And essentially we have that AC is an H because of this property. And so when I have the AC is an H, I can just flip that to get that the original guy is also in the group. Right. Associativity is usually you don't have to prove associativity. Well, you don't have to quote unquote prove associativity. We usually say that associativity is inherited from the group above. Or we say that it's inherited. And what I mean by inherited is because everything is associative from the original G, now I'm just moving to a subset. And so if I'm just moving to a subset, I'm still going to have the same associativity. It's like I'm taking elements, I'm just ignoring things that aren't in G itself, right? So associativity pretty much always is inherent, right? The integers are associative because the real numbers are associative, right? I mean, it's not like I'm suddenly using numbers that aren't real. Because the real numbers are associative, I still have that property when I restrict it to the integers, right? So usually when I'm talking about subgroups, associativity is easy, is always inherent. Number two, right? Take A to be equal to A and B equal to A from this, right? So we set these as both A. We'll see that since this is true for every element of H, then A inverse, in other words, A inverse is equal to E, but by definition, A inverse is in H. So therefore, E must be in H, right? And we can do something very similar for the inverse. So for the inverse, we'll look at this and we'll say that, okay, we essentially want to show that we flip these two and then B A inverse will be in H, right? That's the idea. I think I might give you that as part of your homework, but that's something good to show because the main question I want to give for your homework is to show that the two-step and the one-step subgroup tests are equivalent, right? So that'll be a good lead up for it. The last thing I want to say is just a few properties. There's a couple of properties. There's usually more properties that people give, but I'll give the more important ones. So properties. The identity is unique. There's only one identity. So here's maybe a short proof of that. And this is a common proof to show that things are unique, right? If you want to show that things are unique, well, pick two of them and show that they must be the same. Right. So let E1, E2 be identities of G, right? Essentially, we can show they're the same because what happens when I take something like AE1 equals to A equals to E2A, but we also said that AE1 must be equal to E1A, for example. There's more to this, but essentially, this will imply that E1 is equal to E2. So essentially, I start with two identities and show that they're the same. And these were arbitrary. So that means that there's really only one identity, right? No matter what we pick, it ends up being the same thing. This is not a formal proof. This is just like a sketch of the proof. If you do want to see the actual proof, I can send it to you guys in an email, just so you can see, or you can look it up. It's a very standard proof to see done. But I just didn't want to take up too much time. There's a similar proof for the next property. The inverse is also unique. Right. In other words, when I take the inverse, there's only ever one inverse for each element. Here's another property. Some people call this the socks and shoes property, and you see why in a little bit. It's the fact that if I take two elements and take the inverse, this is equal to A inverse. We call it socks and shoes because obviously you have to put on your socks before your shoes, but when you do it the opposite way, you have to take off your shoes before you take off the socks, right? They flip. That's the idea, right? This is easy to prove, and let's maybe see it real quick. What does it mean to be an inverse? We'll prove it by the definition. An inverse means that when I multiply it by the when I multiply an element by its inverse, I get back the identity. So let's see what happens when I take the element AB and multiply it by B inverse A inverse. Right. because this is an element. I have associativity, so associativity lets me regroup this. So to be precise, I have another set for here, right? But what's any element times its inverse? That's the identity. But then same thing, identity times any element is itself. So this gives A times A inverse, which is the identity, right? So since I multiplied this by this and got back the identity, and since we also know the inverse is unique, that means this element must be the inverse of AB, right? So that's why we say AB inverse is this guy, right? So this would be a proof that this is the inverse of this. Now, some of you might be asking, wait, there must be some certain property that tells us that, oh, this is equal to A inverse B inverse, right? Well, before that, maybe this is more of a definition, so right over here. We say a group is what we call abelian, or we'll say like G is an abelian group, for example. But we say a group is abelian if for every, and let's say G, for every A, B, and G, AB is equal to BA. In other words, it's commutative. So the word abelian just means commutative, because you notice that commutative was not part of the definition of a group, but it's a very common thing we have, right? So the real numbers are commutative, the integers are commutative under addition and multiplication once you take out 0, right? These things, 1 plus 2 is 2 plus 1, 5 times 4 is 4 times 5, nothing changes, right? So these are abelian groups. They have, we say abelian instead of commutative, right? So you see some of the very, very old books talk about a commutative group, but really you just hear people call it abelian, right? So if you ever use the word abelian, you're referring to a commutative group. And so that's where this comes in. If G is abelian, and maybe this is kind of a theorem that you can try proving or look up, or I can give this to you next time if people want. If G is abelian, then for all A, B, and G, A, B inverse equals A inverse B inverse. In fact, I can make this even stronger now that I think of it. Instead of an if then, I can make this an if and only if, right? G is abelian if and only if I have this property. In other words, this goes both ways. If G is abelian, I have this property. Obviously, that makes sense, right? If it's abelian, then I get to this part, which I know for all A and B or any group, right? I can just take these two elements and flip them, right? And I immediately get what I want. That's the obvious direction. It's the backwards that's not going to be obvious, right? If I have this property, how can I get that the entire group is commutative, right? So that's a theorem that you might prove. So these are some properties of groups. So we'll stop here for now. This was kind of a quick introduction to groups and some of the things you might see within groups. So next time we'll formally define and look at some examples of types of groups. So we briefly talked about the dihedral and the symmetric group today. We'll go into a bit further, more of a definition for those. And then we'll talk about isomorphisms a bit more formally, right? We'll say how we can define isomorphisms. And we'll probably start Wednesday with kind of an extension of functions, right? So we talk about how we can have functions on sets. But now we don't have sets, so how can we define a function? Well, there are ways to define functions on groups, right? There's a new analog that we have functions when we're working with groups instead of set functions, and we'll see what those look like. All right, so we'll stop here for now. I will send out a homework either today or tomorrow over some of this introductory group stuff, and then we will probably finish up with algebra on either Friday or Monday. My current plan is to finish this up on Friday, and that should be a good introduction, and then move on to analysis next week. But we'll see how that goes. because honestly, like, you know, you can get an entire semester's worth of algebra, right? And I want to give you guys a good representation of it, right, in like 3 lectures. So I'm not going to cover everything. That's why I'm also not doing every single proof like I would normally do in a proper course. You know, if I was teaching a course in algebra, I'll be fleshing out these proofs a lot more, right? But because we're trying to, you know, condense it and do multiple different sections across multiple different fields of mathematics, we'll kind of like, you know, we'll relax on proving everything. And if there's something you want me to prove, let me know and I'll show you. But for now, we're just gonna kind of condense everything. I'll give you quick proofs if they are quick, or proofs of important theorems and stuff like that. But other than that, I want to just kind of give you what you would see in an algebra class, and or what are some things that are important to know. And then if you ever want to take a class like that, that's when you formally go into deciding, okay, let's prove all these things. All right. In that case, I will see you guys on Wednesday.